When you scrub through a 4K video timeline or load a massive open-world game, your processor isn't pulling that data directly from the hard drive. It's pulling it from the system memory, the RAM, at gigabytes per second. A standard memory stick looks like a flat piece of plastic and silicon, but dive down to the nanometer level, past the black epoxy, and you enter a microscopic grid holding upwards of 8 billion individual transistors. Designing these chips involves a monumental battle against physics, utilizing advanced mathematics and very large-scale integration engineering to maintain stability at the atomic scale. Processors use memory for everything, but not all memory is built the same. Cache memory built directly into a CPU is fast, but it requires 6 transistors to store a single bit of data. That architecture takes up too much physical space for high-capacity storage. System memory relies on a more space-efficient approach. Instead of 6 transistors, dynamic RAM uses a 1T, 1C layout, 1 transistor and 1 capacitor. Think of the capacitor as an analog bucket. When it's filled with an electrical charge, the system reads a binary 1. When the bucket is empty, it reads a 0. The transistor acts as a gatekeeper. It is a microscopic switch that dictates exactly when electrical charge is allowed to flow into or out of that capacitor bucket. A single 1T1C cell is useless on its own. To create usable memory, this specific cell structure is duplicated millions of times and arranged into a vast rectangular matrix of horizontal rows and vertical columns. The horizontal rows are connected by metal traces called word lines. Driving a specific word line high activates every single transistor across that entire row simultaneously. With the transistors open, the capacitors dump their charge down the vertical columns, known as bit lines. At the bottom of these lines, sense amplifiers catch these incredibly faint voltage changes and boost them into a readable digital signal. DRAM is a highly volatile analog system of microscopic physical buckets orchestrated to simulate digital ones and zeros. To understand why it's so volatile, we have to look past the grid architecture and examine the semiconductor physics happening at the p-n junction. Applying a voltage to the gate of a transistor forces electron hole pairs to migrate. This physical movement creates the channel that allows current to flow. But solid materials at this scale are imperfect. The capacitor cannot hold its charge indefinitely. Electrons slowly seep out, creating leakage current. Left alone, the data vanishes. This leakage is why the memory is called dynamic. The system has to constantly read the fading charge and rewrite it, refreshing every single cell every few milliseconds to prevent total amnesia. For decades, the industry followed the trajectory of Moore's law, shrinking these components to pack more gigabytes onto a single stick. Today, we are manufacturing transistors below the 10 nanometer scale. At that size, classical physics breaks down, and we hit the quantum wall. The physical barrier holding the electrons back becomes so thin that particles bypass it entirely, a phenomenon known as quantum tunneling. The electron disappears from one side and reappears on the other, triggering a data error. Managing this requires new materials. Engineers introduced high-K metal gates to thicken the barrier without losing performance, and shifted to 3D FinFET structures to wrap the gate around the channel, choking off the tunneling effect. Scaling RAM requires manipulating atomic structures to force quantum mechanics to behave. In the early days of computing, engineers could wire a circuit by hand. Today, routing billions of sub-nanometer components manually is biologically impossible. The entire semiconductor industry relies on the electronic design automation, or EDA, software ecosystem. It is the invisible layer that makes modern VLSI engineering a reality. The process starts in environments like Cadence Virtuoso. Here, engineers drafting the fundamental circuit schematics, designing the logic, and mapping the initial physical layout. This waveform graph shows tools like Synopsys H-Spice performing rigorous timing analysis, ensuring high-speed signals arrive perfectly in sync. Before manufacturing, Mentor Caliber performs design rule checks, hunting down any layout choices that violate the laws of physics. Once verified, tools like Cadence Innovus or Synopsys IC Compiler take over for the place and route phase. Algorithms physically map the millions of microscopic copper wires connecting the billions of components.
Engineers then deploy custom Python or MATLAB scripts to chew through terabytes of simulation data, optimizing the design to ensure the highest possible manufacturing yield. A finished RAM chip is the physical manifestation of millions of lines of predictive code and mathematical algorithms. The finalized software design is exported as a massive file and sent to fabrication giants like TSMC or Samsung. Fabrication happens inside clean rooms so sterile that a single speck of dust dropping onto a wafer would destroy millions of nanoscale transistors instantly. The layout is printed using extreme ultraviolet lithography. Highly specialized invisible laser beams strike a reflective silicon wafer through a patterned mask, burning the nanometer grid directly into the surface. The chip is built upwards. Multiple layers of metal interconnects are deposited on top of the transistors, wiring the components together like a microscopic multi-story city. Foundries enforce strict design rules at the 5 nanometer and 3 nanometer nodes. The margins for physical error are functionally zero. The direct result of this process is a highly engineered silicon wafer containing hundreds of individual RAM dies ready to be cut and packaged. The fabrication stage is the ultimate test. It is where theoretical physics and EDA software simulations are forged into tangible reality. Every individual die leaving the fabrication line must first pass through intense wafer probing and electrical testing before it can be packaged. Engineers deploy functional tests called March algorithms. The software systematically writes and reads ones and zeros across every single cell, hunting for any physical fault that leaves a bit stubbornly stuck. Surviving chips enter burn-in testing, subjected to extreme voltages and severe thermal limits. The goal is to force weak silicon to fail immediately in the factory, guaranteeing it won't fail in a user's PC. Throughout this entire life cycle, the designs adhere to JEDEC standards. This ensures that a memory module fabricated in Taiwan interfaces flawlessly with a CPU designed in California. Eventually, that chip is packaged, shipped, and slotted into a desktop motherboard. The system powers on, and the memory controller begins issuing commands. The simple act of installing RAM is the culmination of decades of labor. Thousands of engineers battling quantum mechanics, pushing EDA software to its limits, and executing atomic precision manufacturing, all to make sure your data is exactly where you need it, exactly when you ask for it.